Hello again, this is MAT 221. This is Mrs. Johnson. This is Unit 3, Section 1, talking about the shortcuts to the derivative. Now, we talked about taking this fraction and rewriting it so that it was broken up as its common denominator over each term of the numerator. So what we'll do here is we'll use our rules for exponents, our exponent rules, to then reduce each term of this new expression. In the first term, we would cancel out one of the x's. In the second term, we would do that too. And remember, the square root of x is equivalent to x to the 1/2 power. And our rules for exponents would say that we would keep the base and subtract the exponents to get x to the negative 1/2. So rewriting this expression, we get f of x equals 4x minus 5 plus 3x to the negative 1/2. Now notice I have not taken a derivative yet here. Now all I'm doing is reducing the fraction using a common denominator. Now I can take the derivative each term by term. The first term of this expression, if you notice right here, 4x, is just a linear function, so the derivative will equal 4. The second term, I'm going to use my subtraction rule, and then the second term is the constant with no variable attached, so the derivative would just be 0. And our third term, we'd use the addition rule here. In our third term, we'd have the constant multiple of 3 multiplied by the negative 1/2, and then subtracting 1 from the exponent using the power rule. So now we're going to find the derivative of this reduced function and get the derivative is equal to 4 minus 0 times 3 times negative 1/2 times x to the negative 3/2, or 4 minus 3/2 x to the negative 3/2. This is sometimes, when we have a monomial denominator, the easiest way to take a derivative. Now, in a couple of lessons, we'll talk about what's called the quotient rule, which we could use here also, but usually when I have a monomial denominator, that is a denominator that only has one term, it's easier to do this method, which is reducing the fraction first and then taking the derivative. All right, let's do another example here. Let's find the equation of the tangent line to this function. Now remember, to find the tangent line to the curve, we need to know the point of tangency, and I'm going to ask you to find the tangent line to the curve at x equals 1. I'm going to rewrite this function by simplifying it first, bringing the x up to the numerator, making it x to the negative 1. Now I'm going to take the derivative term by term. I get 12x to the third minus 4x minus x to the negative 2. Then when I say, okay, when x is equal to 1, f of x is equal to 2. When I put 1 into the original function, I get 3 minus 2 plus 1, which equals 2. And when I put 1 into the derivative, I get 12 minus 4 minus 1, which equals 7. So now I know that here's my equation of my tangent line to the curve. Y equals, or y minus 2, I could say y equals 7x minus 7 times x minus 1 plus 2, or y equals negative 2, y minus 2 equals 7 times x minus 1. Notice I'm putting each one of these values into my equation to get my equation of my tangent line to the curve. This is the tangent line to the curve at x equals 1. Let's try another one and take the first 4 derivatives. Remember, we can take derivatives as many times as we want to. Taking the first derivative, I would get 3x squared minus 10x, using the power rule, the addition rule, the subtraction rule, the constant multiple rule, and the constant rule. Taking a second derivative, I'd get 6x minus 10. Taking a third derivative, I'd get 6, using the linear rule. And taking a fourth derivative, I'd get 0. Now, we'll find that this will always occur, that the derivative will eventually become 0 if I have a polynomial function. If I don't have a polynomial function, this does not always happen. Matter of fact, it seldom happens. But when I do have polynomial functions, my derivative will eventually lead toward a derivative of 0. Our next rule is the rule for the derivative of e to the x. And unlike any other function that we study, this unusual function once again is unusual in that when I take the derivative of the function e to the x, it is its own derivative. It's one of the few functions, actually one of 2 functions, that is its own derivative. So e to the x is its own derivative. Now notice it's just e to the x here. No coefficient, no power other than x. So just e to the x. It is its own derivative. Another rule for exponentials is called the exponential rule. If we want to know the formula for the derivative of any exponential that has any base, not just a base of e, but any base of a to the x, the derivative of exponential functions are a to the x multiplied by the natural log of its base. In other words, it's very, very close to the derivative of e to the x, but it is, we take the function itself and then we would multiply by the natural log of its base. Now if you put e, by the way, into this formula, you would say, well, the derivative of e to the x is equal to e to the x times the natural log of e. But we know from our previous math experience that the natural log of e is actually equal to 1, so that's why the derivative is itself. So let's find some derivatives. What would be the derivative of this expression? The first expression would be 2 times 3 to the x times the natural log of 3 plus 5e to the x. Notice this uses the constant multiple rule, then the exponential rule, which is itself times the natural log of its base, plus we're using the sum rule, so we plus. This is the constant multiple rule times e to the x, so the constant multiple comes to the front, and then I take the derivative of e to the x, which is itself e to the x. Let's try a couple more. Y equals 2e to the x minus x squared, the derivative, 2e to the x minus 2x. Let's try another one. Take the derivative of 2 to the x, that's an exponential function. It is itself times the natural log of its base, plus the 5 is a constant multiple I would bring to the front, and then I would take the derivative of x squared, which is 2x. 5 times 2x would give me 10x. Then I'm going to use my addition rule here again, plus, but then we just have a constant of 3. The derivative of a constant is 0. So the derivative of this function is 2 to the x times the natural log of 2 plus 10 to the x. How would I take the derivative of this function? I would take that x to the third and bring it up to the numerator. So I would rewrite this function first. The derivative of 2 to the x is itself times the natural log of its base. 2 times x to the negative third would be negative 2 times 3, which would be negative 6. And then when you subtract 1 from the exponent, would be -4. -3 minus 1 would be -4. This one's a trick question. If you look at this one, be careful. E is a number, pi is a number raised to a number is just a number, and the derivative of a number we know by itself with no variable, notice there's no variables there, is just 0. Here we have the number pi raised to the x. This is an exponential function, so the derivative, negative pi to the x times the natural log of pi. Now, the position of an object in meters is given by the s function, where s is equal to -4.9 t squared plus 5t plus 6 in seconds. Find the velocity and the acceleration of this function for this object. Remember we said earlier in Unit 2 that the first derivative of a position function is the velocity function. The second derivative of a position function is the acceleration. So the velocity will be the first derivative of the position function, which is -9.8 t plus 5 meters per second. And remember, derivatives have fractional units. It is change in output unit over change in input unit. And then if I take the derivative again, this will give us acceleration. So acceleration is equal to the derivative of the velocity, which is the second derivative of position, which the derivative of this linear function would simply be the slope, which is -9.8. And then again, my output units is meters per second, and my input units is per second. So I would have meters per second, which is meters per second squared. This, by the way, should look familiar to us as the acceleration due to gravity. That finishes up section 3.1. Have a good night.